Good afternoon, everybody. Thank you very much for your presence here today in one more activity of the 13th Summer Workshop in Mathematics, promoted by the University of Brasília. We are very glad to host you all in our conference. It's with great pleasure and honor that I introduce our next plenary speaker today, Professor Carolina Araujo from IMPA. Carolina Araujo is a researcher at IMPA, and she collects several prizes and honors in her CV due to her impressive work in algebraic geometry. I will not describe all of them because I would spend several hours describing them, but I would like to point out that last year she received the Ramanujan Prize awarded by ICTP. Carolina Araujo is an outstanding researcher in the area of algebraic geometry, with many important and brilliant contributions in this area. Today, she will talk about symmetries in algebraic geometry and Cremona transformations. Thank you very much for accepting our invitation, Carolina, and you can talk. Thank you. You can present your talk.
Thank you, Jacqueline. Thank you for the very generous introduction, and also thank you for the invitation. I'm very happy to be here, and I would like to. So today I want to talk about symmetries in algebraic geometry, in particular Cremona transformation, which I will introduce. So can you see my? Okay. So here is my slides. So I put here a picture of UNB so that we feel a little bit more in this very nice environment. I wish I could be there in presence now, but okay, this is what we have for this year. And so first, let me just introduce the topic just by putting these pictures that are here to just give you an idea of what I mean by symmetry. So I think in any area of mathematics, when you are studying a certain objects, it's often very useful to understand its symmetries. And in our particular setup, we would like to understand symmetries of complex projective varieties. So these are compact complex varieties defined by polynomial equations that live in a certain natural ambient space, which is the projective space. So what do I mean by symmetry? So the first notion of symmetry, and probably the most natural one in algebraic geometry, is that of an automorphism of a projective variety. So if you have two projective varieties, X and Y, so let me define what I mean by a morphism between them. So this is just a map between X and Y that can be given locally at every point by polynomial coordinates. So this is the notion, a natural notion that we consider in algebraic geometry. And now, once you have this notion, you can have the notion of an automorphism. So this is just a morphism from X to X, which has an inverse. And the automorphisms form a group under composition. So this is the automorphism group of a projective variety. And let me give you some examples. So the first one and the easiest one is that of the projective space. So a projective space is often given by a set of n+1 coordinates. And the automorphisms of the projective space are precisely those given by invertible linear maps. So this is just PGL n+1 over C. And so this group is very well understood. And in particular, it is a Lie group, a linear group. And okay, in general, if you have a complex projective variety, the automorphism group of X has a natural structure of a Lie group. And so we can look at the connected component of the identity. So this is a complex algebraic group. And And so we can sort of split our automorphism group in two pieces. So the connected component of the identity, which is a complex algebraic group. So that means it's not only a group, but it has a structure of a complex variety. And the quotient is a countable discrete group. So the structure of this discrete part can be rather complicated. And in general, so let me just give you another set of examples where you see these two different pieces of the automorphism group. So let me start by looking at algebraic curves, projective curves. So complex projective curves are roughly just Riemann surfaces. And those are classified by their genus G. So I just put this picture here, and I hope you attended Cecilia's talk yesterday. So many of the subjects that she discussed are going to reappear in this talk. So the first instance of that is this trichotomy between genus 0, genus 1, and genus greater or equal than 2. So this trichotomy is natural from many points of view. So for instance, in term group, so we have this division in these three cases according to the fundamental group of the Riemann surface. So the first one is just the sphere, the second one is just the plane, and sorry, this is okay, yeah. So genus 0, genus 1, and genus greater or equal than 2. And also, in terms of curvature, this is also a natural subdivision. So we have a positive curvature, zero curvature, and negative curvature. And also, Cecilia explained to us yesterday that this division is also natural from the point of view of the Diophantine geometry. So in the terms of number theory, some Diophantine equations, they give rise to certain Riemann surfaces or projective curves, and the behavior of the rational solutions to this equation also depend on the class, on the genus, on which of these three classes the curve belongs to. And now we will see that from the point of view of the structure of the fundamental group, from the structure of the automorphism group, we also have this trichotomy. So the first one, genus 0, the automorphism group, as we saw, is just PGL2C. So this is a variety and an affine variety. So it is a natural structure of algebraic variety. The genus 1 case, so this is the torus. So this is the torus itself has a structure of a group. So if you think of the torus as the quotient of R2 by a lattice, so this is just given by you can think of the group structure as in the one induced by the complex plane, by addition. And then in this case, the countable discrete part is in fact finite, and we know very well, so this can be Z2, Z3, and Z6, and we know which curve, what is the discrete part for any given curve. So this is very well understood. There is a difference, even though for genus 0 and for genus 1, in both cases, the connected component of the identity gives us something non-trivial. So we really have something of positive, an algebraic variety of positive dimension. There is an important distinction between these two cases. So the first one, the automorphism group is an affine variety, while in the second one, it is the connected component of the identity is a projective variety, is the elliptic curve itself, the curve of genus G. And finally, when the genus is at least 2, then the automorphism group is finite. Okay, so let me give you another set of examples. So in general, so now we're going to move to higher dimensions. And in higher dimensions, we will come back to this later on, but there is a program to classify projective varieties based on autonomy. But in general, in higher dimensions, a variety will be built up from pieces from these three classes. And the automorphism group will actually see these different pieces in general. So let me just give you an example, another set of examples, which is that of smooth hypersurfaces. So a smooth hypersurfaces is just a projective, an algebraic variety in a complex projective space that is defined by a single equation. So in general, when you consider a projective variety, it can be defined by several polynomial equations. And of course, in general, the more polynomials you use to define the variety, the more complicated this variety is going to be. And hypersurfaces, in a certain sense, are sort of simple, simpler to understand than generic projective varieties. And in this case, there is this old theorem by Matsumura and Monsky that tells us exactly what is the automorphism group of this hypersurface. So except for two cases, which is n, which is the dimension equals to 1 and degree 3. So this is our plane curves of degree 3, or n equals 2 and d equals 4. So this is a surface of degree 4. So except in these two cases, all the automorphisms of the smooth hypersurface is given by restriction from a linear automorphism of the ambient space. So this is what I wrote in symbols by writing a surjective homomorphism from the group of automorphisms of the projective space that stabilize X, and the restriction gives you an automorphism of X. Okay, so now let's try to understand these two exceptions. So the first exception is the case of an elliptic curve. And so the degree 3 in a curve of degree 3 in P2 with no singularities is an elliptic curve, a curve of genus 0. And we have already seen that in this case, the automorphism group contains a copy of the curve itself. And in general, this part cannot be in general induced by an automorphism. And the other case is the case of a quartic surface. So this is an example of the object that Cecilia considered yesterday, which is a K3 surface. So in this case, the automorphism group of the surface is discrete and possibly infinite. Actually, so it can be finite and can be infinite and non-abelian, and in the wild of K3 surface, of quartic K3 surfaces, all these possibilities occur. And so in these cases, they are, in general, these groups are infinite, while in both cases, the image of the restriction homomorphism from the group of automorphisms of the ambient space that stabilize X to the automorphism group of X is finite. So the question that I want to leave you here is, so if they are not induced by the ambient space, where do these automorphisms come from? So so this is a sort of a vague question, and we will come back to that at the end of the talk. But right now, I would like to change gear, and now I want to tell you why maybe in some situations the automorphisms are not the correct notion of symmetry in algebraic geometry. So now I will talk about another subject, which is birational geometry. So this is, I can say that this is my main field of research, and I will explain this picture very soon. So birational geometry is an area of mathematics that wants that in a certain ways to classify projective varieties. So let me discuss the classification problem in algebraic geometry. So in dimension 1, so that is projective curves or Riemann surfaces, as I said, we have this nice trichotomy. And so we have a discrete invariant, the genus, that sort of classifies the Riemann surface topologically. And once you fix the genus, there is a moduli space parametrizing curves of genus G. So this was already introduced by Riemann himself, who in his terms, he was fixing the topological type of the Riemann surface. So that is, you fix the genus. And Riemann was interested in understanding what are all the possible complex structures that you can put in this surface. And so he noticed that the space of such complex structures varied in a certain number of parameters. So this is what nowadays we call a moduli space of curves of genus G. So different complex structures are equivalent from the point of view of algebraic geometry of different isomorphism classes. Okay, now let's go to higher dimensions. And it turns out that in higher dimensions, classifying up to isomorphism is really not the right thing to do, and this is because there are way too many isomorphism classes. So let me try to explain to you why there are isomorphism classes, and I will explain to you by describing a fundamental operation in algebraic geometry, which is the blow up of a point. So let me just give you in very concrete terms. I will explain to you the blow up of the projective plane. So before I give you the formulas, the precise formulas, let me tell you conceptually what the blow up does. So the idea is that we start with the projective plane, and we would like to make a modification of our plane by removing one point and replacing it by a curve that parameterizes all the possible tangent directions to this point. So this is what this picture illustrates. You replace the point by in the sense of P1, or this line that is parameterizing these tangent directions. So in the plane, you see all the tangent directions to a point, and then you see that when you lift to the surface, they do no longer meet. They meet this central line in different points. So in concrete terms, so let me fix the point with projective coordinates 0, 0, 1. And now the map in blue from P2 to P1 is just the projection from that point. So I take this point, I take a line that does not pass through the point, and I just project from this point onto the line. So in projective coordinates, it's given in as I wrote in blue, a point with projective coordinates x, y, z is mapped to the point with projective coordinates x, y. So this map is defined everywhere in the plane except at the point P from which you project. So you see that each line through this point is going to be contracted to a different point of P1, and so this point does not know where to go. So this is really not defined there. So what we do is we remove this point, we consider the graph of this map, which is something contained in P2 cross P1, and then we take the closure of the graph. So if you take the closure, then you see that we obtain this projective variety, which I call x tilde, and you can check that it has exactly the properties that I said. So outside the point, the map is just an isomorphism because it's f, and over the point P, you get a P1 parameterized by tangent directions. And so here, we usually denote by E. E stands for exceptional, so this is the exceptional line over P. And if you remove this exceptional line from x tilde, and you remove the point from P2, then you actually have an isomorphism. So you just replace the point by this P1. Okay, so more generally, I can not only blow up a P2 at a point, but I can blow up any variety, any projective variety at any point, and even more generally, I can blow up any projective variety along a proper subvariety. And in general, what I have is that if I look at the complement of this center of the blow up, so if I remove its inverse image, I have again an isomorphism. And then normally I replace this variety Z by some bundle that is parametrized in the normal directions at each point of Z. So notice that if we try to do this, to make this construction starting from a curve, we don't get anything new because we remove a point from the curve and then we replace it by all the tangent directions at that point. But there's only one complex tangent direction to a curve. So this construction only starts to make sense in higher dimensions. And that is why there are too many isomorphism classes. I could start with P2 and blow up a point and then choose another point and blow it up and do any finite sequence of blowups. These will lead to different surfaces. So we see that there is an uncountable class of isomorphism classes that we obtain just from P2. And so in general, the classification problem is going to be a bit different. Instead of classifying varieties up to isomorphism, we are going to have another equivalence relation, and which is called birational equivalence, and we will want to classify varieties up to birational equivalent. So let me define this. So we say that two projective varieties are birationally equivalent if they have dense open subsets that are isomorphic to each other. And in this case, now the problem of birational classification becomes the following. So there are two steps. So in the first step, if you give me a projective variety, the first thing I want to do is to find a simplest representative in its birational class. So this is what we call a minimal model. For instance, if I had P2 and I had the surface obtained by blowing up a point in P2, it's very easy to argue that P2 is simpler than its blow up. So in this case, what we would do is we would choose P2 as a simplest representative, although there are other possible choices. So I will come back to that. And then once you do this once you perform this first step, there is a second step, which is to construct moduli spaces of minimal models with some fixed discrete invariant. Now, for the sake of this talk, I will concentrate on the first step of the problem of birational classification. So this is achieved by the minimal model program. So the minimal model program actually does that for us, at least in many cases. So given a projective variety, we find a simplest representative in its birational class. So for curves, as I mentioned, this was just done by Riemann in the 19th century. And then this is because birational equivalence and isomorphism is the same thing in this context. Now, in dimension 2, this was done by the Italian school in the early 20th century. And it is really what you do is just you look for a blow downs, and then you start to blow down your surface until you cannot blow down anything anymore. And this will be a minimal surface. In dimension 3, things become much more complicated. So the operations that you have to do to go from your given variety to a minimal model are much more complicated. And sometimes it's hard to show that they exist and even that the steps of this program terminate. So in dimension 3, the program was proved to work by Mori. Well, there were contributions by many mathematicians, but it was really completed by Mori in this very fundamental paper of 1988. And this work actually yielded him the Fields Medal in 1990. So this is really a very important work. And much more recent, in 2010, we have a partial program in arbitrary dimension. So this is not a complete program, but it's good for many purposes. And so this was achieved by work of Birkar, Caccini, Haken, McKernan, and you may recognize Birkar also received the Fields Medal in 2018. Okay, so this is what the minimal model program does for us. And once you already have the minimal model, then one question that is very natural is to understand which varieties are in the birational class of Pn. So Pn, in a certain sense, is the simplest projective variety. And the question is, and a variety is said to be rational if it is birational equivalent to Pn. So if it can be transformed into Pn by some algebraic operations. And a very important and central problem in birational geometry is to decide which algebraic varieties are rational. So, and to make this problem even more precise, let us look at it for hypersurface, which we have already encountered. So for which degree and dimension, d and n, is the generic hypersurface of degree d in dimension n rational? So this problem is not completely, so this problem is it's very much open. There are some easy constraints. So there is this necessary condition that it's actually, that is that is easy to prove, which is that for a hypersurface to be rational, its degree must be very low. So it has to be at most n+1. And so this result is easy to obtain just by looking at top differential forms. In any case, so if we want to find examples of rational hypersurfaces, we have to look at small degree. And so let's look at quadratic hypersurface. And in this, so a quadratic hypersurface is just a projective hypersurface in Pn+1 that is defined by a polynomial, a homogeneous polynomial of degree 2. So this is just like a hyperboloid, or that we are used to encountering. Now, in this case, it's very easy to construct a birational equivalence between the quadratic and Pn. And this is just what we usually call the stereographic projection. So one important property of the quadratic is, because the degree of the defining polynomial is 2, if you take a generic line in the projective space, it will meet our quadratic hypersurface precisely in 2 points. And so we use this property to define the stereographic projection. So we choose a general point in a quadratic and then just project from this point into a hyperplane Pn. And so it's easy to check that this is a birational map. And so now let's look at the next case, the case of cubics. And here we have a very important open problem in algebraic geometry. So already for degree 3, starting in dimension 4, it is not known whether the generic cubic hypersurface is rational or not. It's very striking that we do not have the answer to this problem. But so there has been lots of activities in this problem, and we have been finding many new examples of rational and non-rational hypersurfaces. But I would say that this would be this is a very striking problem in birational geometry. And let me just now say, if we want to attack this problem, then we want to find, so how can you check if something is rational or not? So we need to find some property that is invariant in their birational equivalence, and then check if this property holds for 2 given varieties, in order, at least to have a necessary condition for them to be birational equivalents. And now we come back to symmetries in algebraic geometry. So from this point of view, from the point of view of this type of problems, automorphism is not the correct notion of symmetry. And let me explain to you why. Well, let's suppose that you have two birationally equivalent varieties, X and Y. And suppose we have an automorphism of X. So this is illustrated in this diagram. So if you just take the composition, if you go around the diagram, you will see that this automorphism of X will not induce an automorphism of Y. Rather, it will induce a birational self-map of Y. And so, and the automorphism group, therefore, is not an invariant under birational equivalent. However, the birational group is an invariant. So the birational group of a given variety X is just the group of birational self-maps of X under composition. And let me say that the birational group has been used to detect irrationality. So, for instance, in the 70s, Skovsky and Manin proved that any smooth quartic threefold, so now degree 4, is irrational by computing its birational group and comparing with the birational group of P3. And so now let me talk about this special group. So in the special case of a projective space, this is called the Cremona group. So a birational self-map of Pn is called a Cremona transformation. And so let me give you some examples. So this is, of course, the group of the Cremona group, say, of the plane, will contain the automorphisms of P2. But it contains many more elements. And this one is, called the standard quadratic transformation. And it's probably the simplest Cremona transformation that is not an automorphism. So it's given in projective coordinates. I gave it in two different ways, which is going to be useful for different purposes. So the first way you can define it as just taking the inverse of each of the coordinates. So we see that it will not, this does not really make sense if sum of the coordinate is 0. So, but in projective space, we can multiply all the entries by the same polynomial. So this is the same thing as writing yz, xz, and xy. So this is why it's called quadratic. And we see easily that this is an involution. So just by the first description, we easily see that the tau square is the identity. And it has this, so this is a sort of a diagram to illustrate what this map does. So you can also check that if you take any of the coordinate lines given by x equals 0 or y equals 0 or z equals 0, this line is contracted to the opposite coordinate point. While at the 3 coordinate points, this map is not defined. So it is only defined at the complement of the 3 points, and it contracts the coordinate lines to the opposite point. So this is a very simple geometry. And even though this is a very simple Cremona transformation, this is enough to generate the whole Cremona group together with the automorphism group. So this is the content of this classical theorem of Neder-Castelnuovo. So Neder was the first one to state it in 1870, but his original proof had a gap. And Castelnuovo was the first one to give a complete proof. And so I should remark that if you give me any degree d that can be as high as you want, I can construct a Cremona transformation given by polynomials of degree, homogeneous polynomials of degree d. So you can have Cremona transformations of arbitrarily large degree. However, they can be factorized as a composition of automorphism, and this is a very simple involution. Okay, so you may think that you know generators, very simple generators. You understand very well the automorphism group, and then you have this one involution that is very simple to describe, and then you may think that you can say anything you want about this group, and this is far away from being true. So, for instance, I just want in the next results to illustrate that some fundamental questions about this group have only been answered very recently. So the first one is the question of simplicity. So Cantat and Lamy proved in 2013 that the Cremona group of the plane is not a simple group. So this is this was a very old. It had over 100 years, was over 100-year old, this problem. And also another problem that, again, started to be considered in the 19th century and was only solved very recently was the classification of all finite subgroups of the Cremona group of the plane. So these are two examples of very basic questions that we could only answer very recently with very strong techniques. And there are also other aspects of the structure of this group that's still not completely understood. And okay, so now let's move to higher dimensions and let's see what is known in this case. So the first, so here, let me just remind you the theorem of Nether-Castelnuovo. And then the first thing I want to say is that we do not have any Nether-Castelnuovo type theorem in higher dimensions. So this was observed by Hilda Hudson in 1927. She showed that for n at least 3, the Cremona group in dimension n cannot be generated by elements of bounded degree. So you cannot have anything similar to the Nether-Castelnuovo theorem. So any set of generators have to have unbounded degree and moreover even be uncountable. So we do not know any nice set of generators for the Cremona group in higher dimensions. Nevertheless, there have been some very recent striking results about this group. So in dimension n at least 3, again, this group is not, the Cremona group is not simple. So in this case, this was proved by Blanc, Lamy, and Zimmerman in 2019. So they produce many surjective homomorphisms between the Cremona group and the cyclic group of order 2. So actually, they produce many such homomorphisms. You can, in some sense, you can prescribe. If you give me any countable set of elements, I can prescribe it to be in the kernel. And this is very different than the two-dimensional case, because even though in dimension 2, the Cremona group is also not normal, it is known that any quotient will have to be infinite and uncountable. And infinite and non-abelian. And here, they constructed a homomorphism onto a simple finite group. Okay, so what are the tools that we have to understand the Cremona group and Cremona transformations in higher dimensions? So we do not have, as I said, a strong factorization theorem as the Nether-Castelnuovo theorem. However, we have a weak factorization theorem, and this is, pretty much one of the strongest tools that we have to understand this group in higher dimensions. So this is what is called the Sarkisev program. So the Sarkisev program is a factorization procedure for Cremona transformations in higher dimensions, or actually in any dimensions. So if you have a Cremona transformation of Pn, you can decompose it as a composition of simple elementary transformations. But there is a subtlety here that these xi's that appear in this factorization, we have to allow them to be other rational varieties. They may not be Pn themselves. While the green maps are very simple, so these are elementary links. For instance, they could be just a blow up of a point. So this is an example of an elementary link. And but the xi's are not always Pn. We have to allow for other spaces in order to have this factorization. And what you allow for is what we call the Mori fiber spaces. So these are the possible outcomes of the minimal model program. So remember, I told you that if you have a rational variety, or if you have any variety, the MMP, or at least, okay, in our context, if you have any rational variety, if you run the MMP, this is going to give you a minimal model, or a simplest representative is in birational class. This representative may not be unique. And the Mori fiber spaces this is just the name for the possible outcomes of the MMP in this situation. Okay, so this is the type of factorization result that we use. And now I would like to go back to the problem that I started with, the problem of understanding automorphisms of smooth hypersurfaces. So remember, I explained to you that the automorphism of a smooth hypersurface is always induced by a linear automorphism of the ambient space, except in the case of elliptic curves and K3 surfaces. And now I want to go back to this question. So where do this automorphism come from? So let's look at the case of elliptic curve. So in this case, as I said, you have all the translations given by the group structure on the curve itself. And they don't come from automorphism, but they do come from Cremona transformations of the ambient P2. So this is a sort of a folklore theorem. It's not hard to prove. You could prove it after a first class in algebraic curves. And now what is much more complicated is the case of K3 surfaces. So in this case, there is this question of, so the question is attributed to Gizzetulin. So I learned from it in a paper of Gizzo. So the question is every automorphism of the K3, quartic K3 surface induced by a Cremona transformation of the ambient space? So actually, Ogizzo, when he addressed this question, he showed that the answer was no. Well, no in general. So he produced examples of K3 surfaces with automorphism group that are not induced by Cremona transformations. But he also constructed examples of K3 surfaces with very complicated automorphism group, non-abelian and infinite, and yet every such automorphism was induced by a Cremona transformation. So it's the question is it seems to be very difficult to grasp. And so I started to work on this problem with Alessio, Corti, and Alex Massarenti. And what I would like to explain to you now is explain the tools that we have been developing to attack this problem. So we want to describe the group of Cremona transformations that preserve S, and then we want to understand this group of homomorphisms. So if you want to understand if a given automorphism is induced by Cremona transformation, then in other words, what you want to know is whether this automorphism is in the image of this restriction homomorphism. So the group the birational group of the pair P3 and S is just the group of Cremona transformations that stabilize S, the K3 surface. And then once it stabilizes S, it will induce an automorphism of S. Okay, so let me explain to you the technique that we have been developing, and this is the notion of volume preserving Cremona transformation. So in order to explain this, I would like to describe another example. Already in the plane, it makes sense. So let's fix a meromorphic volume form on P2. So this meromorphic volume form, dx over x, wedge dy over y. So this meromorphic volume form has simple poles along the 3 coordinate axes, and it's non-vanishing elsewhere. And we want to understand the group of Cremona transformations of P2 that preserve this volume form. So this problem was studied by Blanc in 2013, and he actually gave a very precise description of this group. So it has the first part of the group, the part in pink and blue, is the part of the group that preserves the torus. So the torus here is just the P2 minus the 3 coordinate axis. So this is just isomorphic to C star squared. So the pink part C star square is just acting by translation on the torus, and the SL2 is just acting by these monomial transformations. Okay, so this part that preserves the torus is very well understood. And again, you have, in order to generate the whole group of volume preserving Cremona transformations, you have to add this Cremona transformation of degree 5. So again, it's an element of finite order, and they generate the whole group. So this is known in this case, and of course, a natural problem is to extend this to projective spaces of arbitrary dimensions. Again, you have this natural volume form on the torus, and you want to understand what are the Cremona transformations that preserve this volume form. So this is a motivation for our general framework. So what we do is we instead of fixing that meromorphic volume form, that natural on the torus, we can fix any meromorphic volume form. And we want to look at the group of birational self-maps of Pn that preserve this volume form, at least up to scaling. Now, if you have a volume form on Pn, then you can look at the hypersurface, the zero minus the pole. So this is just a cohomology class that, okay, the zeros is just to take the hypersurfaces where this volume form vanishes, and the pole is just where it has a pole. So this gives a cohomology class in Pn, and this is as a cohomology class, this does not depend on the meromorphic volume form that you choose. And then conversely, if you give me any and this is exactly minus n+1 times a hyperplane section. So conversely, if you give me any hypersurface of degree n+1 in Pn, there exists a unique up to scaling meromorphic volume form whose cohomology class is precisely, here I probably made a mistake, I wanted to say minus x. So it has poles, again, along x, and it does not vanish anywhere else. So sorry, here there should be a minus. And so the problem that we have been addressing is to describe this subgroup of the Cremona group of volume preserving Cremona transformations once you fix the form corresponding to x. So let me just put here, so I stated two problems that seem a bit different. So first I said that if you describe, I want to describe the group of Cremona transformations that stabilize S, and then to understand the restriction homomorphism. And then I said that I want to describe the subgroup of the Cremona group of Cremona transformations that preserve a certain volume form. So what this has to do, what one problem has to do with the other, and this is the very there's a sort of crucial observation, is that if the hypersurface X is mildly singular, so you can think of this as if it is smooth, then these two groups are the same. So the group of Cremona transformations that preserve the volume form is the same thing as the group of the Cremona transformations that stabilize the corresponding hypersurface. So just for those that are more acquainted with notions from birational geometry, the correct notion of mildly singular is to have canonical singularities. But okay, this is not important. And so now, okay, so now I should tell you, so why this is, this remark, once you know the techniques from MMP, it is not difficult to prove this equality. But this observation that this group of birational maps that stabilize this hypersurface can be seen from the point of view of volume forms opens the whole world of the MMP for us. So once we phrase things in terms of differential form, we are in the scope of MMP. And so we have all the techniques from the MMP at our disposal. For instance, I told you about the Sarkisev program that provides a factorization between for Cremona transformations. And for volume preserving Cremona transformations, we have a similar result. So this is a theorem by Corti and Kalogiros from 2016. They show that any volume preserving birational map between Cremona transformation of Pn. So here I'm fixing some meromorphic volume form, and then I ask that the Cremona transformation preserves it. Any such volume form is a composition of volume preserving Sarkisev links. And so, having said that, let me just state our some of our results in this project. So first of all, we prove that if you take your hypersurface, so now X again is a hypersurface of degree n+1 in Pn. So if X is very general, so if you pick it at random, then the group of volume preserving Cremona transformation is nothing but the group of automorphisms of Pn that stabilize X. So, so if you want to use these tools to produce new subgroups and interesting subgroups of the Cremona group, you have to pick a special hypersurface. So what I say very general, just for those that are more acquainted with algebraic geometry, what I mean is that it is smooth and it satisfies this Lefschetz type property. So the cohomology, the second cohomology is is obtained by restriction of that of the ambient space. And okay, so as I said, if you want to construct some interesting examples of subgroups of the Cremona group, you should pick some special hypersurfaces. And then we started to do this. So there are two directions that one could take. So one of them is to allow singularities, so that X is not smooth, or to allow this non-Lefschetz type hypersurfaces. So these are two directions that will produce interesting examples. So we have been investigating the first direction. So we started to look at singular surfaces, first by singular quartic surfaces, and then we investigated how allowing for more and more complicated singularities will make the birational geometry of the pair P3 and S more complicated. So let me just give you an example. So if you take a quartic surface with one singular point, then in suitable projective coordinates, it's given by this equation that you see. So this surface is singular at one point, and locally analytically at the point, the singularity looks like the cone, the green cone that I have in this picture. So this green cone is given by the coefficient. So here the equation of S is given by these three polynomials, A2 of degree 2, B3 of degree 3, and C4 of degree 4. And so this A2 is just defining this green cone, and this is the singularity type at P. So in this case here, again, this singularity is mild enough so that our group of birational Cremona transformations that preserve the volume form is the same thing as that stabilize the surface. And so we have this restriction homomorphism. And now first thing we have to do is to understand this birational group of S. So first I had automorphism when X was smooth. Now, if you allow for singularities, once the Cremona transformation stabilizes S, it may not induce an automorphism, but just a birational self-map. And but this group is actually very easy to compute. So if you look at the formula that defines the surface, you see that if you give me any x1, if you give me, say, generic x1, x2, and x3, I can just solve this equation in x naught, and I will have, in general, two solutions. So there is an involution of the surface that switch these two solutions. So this involution is called, this birational involution is called tau. And it's not hard to show that the group of birational self-maps of the surface is just generated by tau. So this is a cyclic group of order 2. And so, okay, so this is what we have. And then you can just I can actually tell you that this homomorphism is surjective by just presenting to you a Cremona transformation that preserves the surface and induces this birational involution tau. So you have to believe me, but okay, this is a Cremona transformation that induces tau on S. And again, you can check that it is an involution. So what we have here is a split exact sequence, which is giving us information about the structure of the group. So in other words, let me just state our theorem B. So here we fix a general quartic surface having one singular point, and the group of Cremona transformations that stabilize S is just a semi-direct product of Z and Z mod 2Z, where this G, we use the Sarkisev program to completely describe this group G. So this is what we call a form of GM over this field of fraction. So I do not want to explain what this is, but if you want, you can ask me afterwards. Okay, so if you are interested in explicit mathematics, actually, I can tell you that not only we gave a description of the kernel G, but actually we can write down exactly what it is. So if I remind you that this is the equation of S, I can tell you exactly what are all the elements of this normal subgroup G. So this is given in coordinates by this formula. So okay, so this is just to know that this is just to illustrate that these methods not only allow us to prove some abstract results, but actually we are able to produce some concrete and explicit mathematics using it. Okay, so let me just, this is my last slide, and I would just like to come back to the problem of automorphism of quartic K3 surfaces. So Cecilia also explained to you many different aspects of K3 surfaces yesterday. So these are really very fundamental and central in algebraic geometry. And so we have a quartic K3 surface, and there is this question: so which automorphisms of S are induced by a Cremona transformation of the ambient space? So as I said, this means that we would like to describe the group of Cremona transformations that preserve the corresponding volume form and understand this restriction homomorphism. So how do we expect to do that in general? So in general, we have, as I said, we have the Sarkisev factorization of our Cremona transformation. And if you look at our surface S, what happens with S when we follow this factorization, then it's interesting that that in most cases, the S does not really see the Cremona transformation. So many of these elementary links that appear in the factorization, they will restrict to the identity on S. So the S will not feel it. However, its very existence marks some curves on the K3 surfaces. And the idea is that each of these elementary links is sort of marking a curve, and these curves must have some very special properties. And so we hope that by understanding better K3 surfaces and the curves that live on it, we can have at least some necessary condition for an automorphism to be induced by a Cremona transformation of the ambient space. And so this is it's a completely open problem, and this is something that we are currently working on. So I thank you very much for your attention, and I'll be happy to answer questions if I can.
Thank you, Carolina, for this wonderful talk. It was very nice and very clear. And now I would like only to recall the audience, if you'd like to do some questions, please, you can write in the chat on the YouTube. And here we have one question from Mohammadi Tahir. And the question is, what's bounded degree in Hilda-Hudson theorem?
So what I mean was the following. So let's go back to the Nether-Castelnuovo theorem. So the Nether-Castelnuovo theorem says that for P2, the Cremona group is induced by automorphisms. So automorphisms are just linear maps, so given by degree 1 polynomials. And the Cremona, the standard quadratic transformation has degree 2. It's given by degree 2 polynomials. So when I say the degree, I mean the degree of the defining polynomials. So what Hilda-Hudson showed was that any set of generators have to have contain elements of arbitrarily large degree. So you can find a sequence of degree going to infinity. But it's even more. I mean, you have to have an uncountable collection of unbounded and uncountable collection of generators.
Thank you, Carolina. And also, Mohammad Tahir, he made another question. Can we use a geometric product, inner plus outer, for determination of automorphisms in projective geometry?
Okay, so I should say that I am not. I am not an expert on the problem on understanding describing automorphism groups. So, for instance, I did that. I was curious to go to MathSciNet and just put automorphism of K3 surfaces, and you get in the title of the articles, and I got dozens. I think it was maybe 77 papers just with this expression in the title. So there are many different techniques that people use to study the automorphism of K3 surface, but I really do not know yet. I hope I'm learning. I'm trying to learn this, but I don't yet know what are the main tools that one uses to understand these automorphisms.
Okay, thanks. There are a lot of people. Thank you a lot for this nice talk. And also we have another question here from John McQuarrie, and he asks, thanks for the talks. I guess the Cremona group of P3 embeds into its profinite completion. Do you know if this group has been studied?
Okay, yes. So thank you for the question. So actually, there are a lot of people studying the Cremona group from the point of view of group theory. And so, and this is going to be another ocean of mathematics. So people, for instance, the Tietz alternative is investigated for this group. So I mean, there is from the point of view of group theory, there is another immense number of results, which I have been trying to follow some, but I'm not a specialist in group theory, and so I do not know what is the status. I know some of the problems that have been investigated, and some of the tools from group theory, but not so much. But I think this type of question is this type of groups of tools are very much used in the theory.
Okay, thanks. So here we have, as I mentioned, a lot of people thank you and congratulating you for the nice talk. And we have no longer other questions, but I would like to thank you very much, Carolina, for this wonderful talk and very clear talk with many draws and pictures. It was wonderful and a great pleasure to us to have you here in our 13th summer workshop in mathematics.
Okay, thank you again, Jacqueline, and thank you for organizing this. I've been following the event, and it's been very, very nice. So I'm really enjoying it. Thank you.
Thank you very much. So bye-bye, people, and see you in the special sessions in the afternoon. Bye.